So global error vs local error. Local error. Okay, so global error means you are solving an ODE, du dt equal to f of u. So let me specify what is known. So f is known. Okay, u equal to 0 is known, and the error is in u numerical minus u analytical, so u itself. So this is global error. And versus local error is basically du dt. Okay, we are just computing du dt, and my u is as a function of t is given, and the error we are looking at is du dt numerical minus u du dt analytical, right? So there are two different problems. Last week we are looking at the local error. This week we are looking at the global error. The global error is more difficult to reduce than the local error, and it turns out stability is the critical link. Okay, so the analysis goes the following. So if we have du dt equal to f of u, and we are writing down a scheme. So for example, in our un plus 1 is equal to a particular linear combination. All right, so let's say un equal to 1 is equal to something times un plus something times un minus 1 dot 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 plus something times f of u at some point, right? Or n minus 1, let's say n. Okay, so how does this operation going to affect the error of our numerical solution? So to answer this question, let's actually rewrite this in a matrix form. Let's write this in un plus 1, etc. up to un. For example, in our previous example, minus 2 is going to be equal to our un minus 3. But now we have an additional term. This additional term is 0, 0, 0 down here, but we have something times delta t times f of un over here. So we have a matrix system with a right-hand side, right? Every time we are adding this particular right-hand side. Okay, and not only that, we can also express the analytical solution like that. We can also express our let's see, this f of u is equal to du dt at a particular step, right? So if you replace this particular the u in the equation with the analytical u, I'm no longer having an equal sign. I'm having an approximately equal sign, right? So let's give actually a simple example. So I have un plus 1 minus un over delta t equal to f of u. But remember, this is only true for my numerical solution. So I should actually be adding a hat onto this to denote numerical solution. So this is exactly equal only for a numerical solution, right? So hat denotes numerical. So that is the one with some non-zero error. Okay, so if you write down our analytical solution, it's not equal, it's only approximately equal to f of u hat. And how big the, f of u hat, how big the approximation error is depend on the accuracy of the scheme, right? Because from the differential equation, I know f of u is exactly equal to du dt at n. So how big the approximation error is exactly how accurate I'm using this derivative approximation scheme in approximating that, right? In other words, my un minus plus 1 minus un over delta t is actually equal to du, let me just write it down, is equal to f of u at n plus o delta t, right? Remember the big O notation for first order scheme. We are making a O delta t error if we plug in analytical solution into the numerical scheme. So that's the first step in most of the error analysis, is plugging analytical solution into the numerical scheme to see how much error we are making per step. All right. So with that, and this we now coming to the second step, is that we are combining the numerical scheme, which is satisfied exactly, with the analytical scheme, which is satisfied to O delta t to the whatever power. We combine them together. How do we combine them? Notice that both have roughly the same formula. So why don't we subtract one from another? All right. Now, by subtracting one from another, what we get is, on the left-hand side, it's un plus 1 minus un plus 1. One is numerical, one is analytical. Minus un hat minus un, one is analytical, one is numerical, over delta t. That's the difference between left-hand sides, right? Okay, the difference between right-hand sides has two terms. One is relating to the f's. One is f of u hat minus f of u. So that's the right-hand side evaluated at numerical and analytical solutions. And then the second term is plus this O delta t. I mean, you can write it as subtract, but like it's really meaning the same thing. Means like there is an error of order delta t. So this equation we now derived by combining analytical and numerical solution has special significance. It denotes how this guy, which is the difference between analytical and numerical solution, we can write it as the error at step n plus 1. How is it relating to the error at step n? And how do we do this term? How do we deal with this term? Well, dealing with this term is simplest if the f of u hat is linear. And if f of u hat is nonlinear, we need a special technique called linearization. And linearization assumes that the analytical and numerical solution are small so that you can treat the f as if it's a linear operator. So this becomes the df du times en, right? So basically the difference between them, again using Taylor series analysis and only retaining the first term, becomes the df du times the difference between u hat and u, which is en. Okay, so here what we see is we have derived a evolution formula for the error, which is en plus 1 would be equal to en plus delta t times df du times en, and then also minus o delta t times delta t, which is what? Delta t squared. All right. So what does that mean? That means every time I perform this forward Euler, I get an accumulation. I get an additional error, that is O delta t squared, that contributed from this very time step. I also carried over whatever error I have in my previous time step. And then I have an additional term that comes from the equation itself, that comes from df du. That's how much the stability of the differential equation itself is contributing to this equation. So these three terms are each is very important. The first term is basically just a carryover from the previous time step, and this is zero stability. Okay, remember forward order only has an eigenvalue of 1, right? So it basically just carries over the previous time step. It's error. If you have midpoint rule, the first term would be having two terms. One is just a carryover, one is carrying over a different component of the area and multiplied by -1. If you have the fourth order scheme, it's not just a carryover, but a carryover multiplied by a factor of 7.8. So the first term is zero stability. The second term we'll analyze later is called eigenvalue stability. It represents how much we are using the stability property of the equation itself.